Hello everyone, my name is Leznik from University of Ulm, and together with my colleagues from the University of Würzburg, today I would like to present to you our work titled SameSame but Dissimilar, Exploring Measurements for Workload Time Series Similarity, where we looked at an automated approach of measuring time series performance measurement similarity and dissimilarity. So first of all, let's look at the motivation of why one would like to do such a thing. So if you look at those 10 measurements presented here, in this case, it would be quite easy also with the naked eye to discern the both two red measurements, right? And if you would use some kind of a mean or some standard deviation approach, you would also see it in the numbers. And so when presented with a measurement like that, we would ideally like to remove or at least look at those two measurements as on their own and not include them in the 8 other measurements, because they would obviously skew the measurements in the wrong direction and present as an outlier. Right, so, but what if the case is a bit more complicated, right? What if we have those 3 measurements presented in different colors, and as you can see here, obviously from the colors, they're basically not in the same group, although they perform similarly. The only similarity here they have is that they perform chaotically, right? So what we would like to ideally do is remove those 3 measurements and look at the 7 other measurements as their one group. But here, as we can see from the data ranges, the mean or some kind of a standard deviation approach might not work so well, because we're basically in the same ballpark of numbers. So there's no ideal or good way to measure the similarity or dissimilarity between those numbers. So if we look at how this is generally done in benchmarking systems and reporting it in time series data, experiments ideally are generally based, and they of course should be based on multiple runs, and the outcome of those runs is generally reported with a mean or a standard deviation, as already mentioned. However, volatile environments presents with a multitude of behavior which can influence those measurements, right? So those measurements should be grouped by their behavior, right? Because we might have some kind of a noisy neighbor effect, which would present as an outlier in one measurement, and which does not reflect the behavior of the system, but rather reflects the behavior of the underlying system which the test is performed upon, e.g. some kind of a cloud infrastructure or something like that. And if we measure a distributed database performance, we would not like that to be included into basically the measurements that we report. Otherwise, the outliers in the measurements skew the results, and what we ideally like to do is to present and report the results in separate groups, which would of course increase the data quality of the data that we present. And the question that we additionally pose here is basically, are the mean and standard deviation even enough for reporting such experiments? This is widely practiced and widely done, but as we've just shown, it might not be the ideal approach for that. Right, so what we would like to have is some kind of an automatic analysis of time series similarity and dissimilarity, which by all accounts is currently missing. So what we've set out to do is first of all look at 6 conferences, the proceeding of 6 conferences for 3 years, so from 2018 to 2020, comprising of the UCC, the ICP, Mascots, Cloud, SOC, and Sigmod, and basically include all the papers published in those. So as you can see, we've totaled over 1,000 papers, and the inclusion criteria was very easy. You just simply had to publish at one of those conferences, and the exclusion criteria for us to look at this work were quite simple. So we basically excluded papers that did not publish any data. We excluded papers that did not concern themselves with performance measurements, or the measurements were not real, i.e. they were, for example, simulated. We excluded work that only presented aggregated values and not time series data. And of course, we excluded papers that did not perform enough repetitions of their measurements. So we would ideally like to have them present with 10 repetitions for each measurement, as again we're dealing with volatile environments, which of course need or call for that amount of repetitions. So this basically left us with a very humbling amount of actually only 3 data sets, which we'll come back to later, but is also a cause of concern, as we might definitely see it. And so what we did further is basically looked at 6 similarity and 6 dissimilarity metrics to be able to measure the, again, similarity and dissimilarity between the single repetitions of an experiment. But the problem here is, of course, that with 12 metrics, it's 12 metrics. This would present with a lot of numbers and make the calculation rather difficult. And so what we did further is basically look at the correlations between those specific measurements. For example, as we see here, if we look at the Kolchinsky-2 metrics compared to the Bray-Curtis metrics, then we see that the correlation is very high, meaning that those two values generally report the same or very similar number when measured for two time series, right? So basically what we can see here is that if we just use one of them, for example, this would be enough for us. While when we looked at, for example, the cosine metrics or the scaled RMSE, we see that they present with much more heterogeneity throughout the metrics, which means that if we look, for example, take the cosine, we will definitely get results that are not similar to the other metrics presented here. And this left us basically with 4 metrics which we can use for all data sets. This would be the cosine, we have Haget's, Kumar Hasselbrook, and the scaled RMSE. As you can see, for some data sets, some measurements presented better, but we've opted to use those 4 because we see them as an overall complete approach for measurements. So basically what we then had, once we turn the similarity and dissimilarity around, so we further only speak about dissimilarity because we simply invert the similarity metrics for easier use when clustering or showing here at with the correlation. And we have 4 values which represent the dissimilarity of 2 experiments between each other. But the problem here also is that if we have only one experiment with 10 repetition, the 4 scores would still yield us with the 4 metrics would still yield us with 180 scores, which is a bit too much, of course, right? So what we do further is we calculate the average dissimilarity between the 2 runs, and then what we have is a single value that represents this dissimilarity between the 2 measurements. And what we then do is we use agglomerative clustering, which is an advantage because it dynamically selects or adjusts the number of clusters. So we do not have to, as similar, for example, to k-means, presented with a specific number of clusters we would like to have. And it works with pre-calculated values. So basically we can use the mean dissimilarity that we've calculated before. And what we basically do is if we see that there's more than one cluster in the experiment, then we can definitely have basically we can definitely see that there were some divergent runs there. Further on, we also would like to have a majority cluster there, so we would like to have one group or one cluster with at least 5 measurement repetitions. Otherwise, we can definitely know that we can discard the run as it is because it's simply too heterogeneous. And we can describe the similarity or dissimilarity in the measurement as the overall similarity or dissimilarity for all the 10 runs, or do it in between the clusters as just said, which basically improves and betters the data quality here, because what we have is we can calculate the cluster gain. So we can definitely see, if we only look at the overall similarity and the in-between cluster similarity, we can see how much better we are in the results that we present when compared to just the overall similarity. And so we invite you to explore our work. We present all the tables and all the approaches on the algorithms of our measurements. And we definitely invite you to look at our supplementary material, which includes some illustrations that I've shown you before for examples of the data sets, and more examples and plots of what we've seen in the data. And of course, we definitely invite you to check out our artifact, which provides you the mean to perform your own measurements. As you can see, we've been evaluated, and the artifact is available and evaluated for all of you to use, and is uploaded on Zenodo. And this brings me to my last point, which is a call to action that we would like to send to everyone. Having combed through over 1,000 papers, we've seen a lot of things that we would ideally not like to see in the research community. So either the authors did not perform enough repetitions, or while they were actually using open data, they did not make their results available or code available. And oftentimes, which was also very, very, I would say, sad and concerning, links to data or code were not available only just after 3 years, while actually 3 years were the oldest conferences we've looked at. So some were from 2019, some GitHub links and so on were not available anymore. So while the links were, or the URLs were in the paper, you could not use the data because there was no way to get to that. So we definitely encourage everyone to use platforms that encourage open data access for a long time, for example, such as Zenodo, which also leaves the work with a citable DOI, and definitely follow that, because this makes the understanding and reproducing your results in your work much easier. And with that, again, make your code available, also the results, and also not only the code and the data you've used, but definitely the results also. And with that, I thank you, and hopefully see you virtually at the SAP conference this year. Thank you and goodbye.